Hello and hi. Okay, for this video I want to talk about the geometric probability distribution. The geometric probability distribution. To explain this and to explain it a little bit more easily, I want to start back to front, and I'm going to talk to you about a scenario where we need it. I'm going to describe it so that this is a little bit easier to get a handle on. I want you to imagine a situation. So you're with a friend and you're betting money. That's what you do with friends, right? Some of us anyway. So you're going to play a game of dice. You're going to roll the dice, and you're actually going to place wagers on how many rolls it takes before you achieve some certain outcome, okay? So let's say that we're interested in getting, I chose a number 4 randomly. And let's say you're betting your friend, or your friend is betting you, some certain amount of money, $10, that the first 4 will be achieved on the third roll. We're going to call that, in probability language, the third trial. What's the probability we should get a 4 on the third trial? Okay, some of you guys are already imagining what this would take and how it would work out, and that's fine, but I want to take it slow and dissect this and put it into very strict form, even though we're going to talk about it casually. I want to be careful and make sure we understand this pretty well. What does this mean to get some certain outcome, which, by the way, we're going to call success in the language of geometric probability? What that means is, for us to get the first success on the third trial, that means we must have gotten a failure up to that. That's an implication. It can't be the first success on the third trial if you weren't failing all the way up to that. If you got a success before that, you wouldn't be getting your first one on the third trial, by definition. So we are obligated to understand that we have a sequence being implied by the question, by the bet, of failure, failure, success. So what we need to do is take the probability of failure and multiply it times the probability of failure again, and then the probability of success, to come up with the probability that such a thing would happen. We can figure this out. Now, we can assume that this is a fair die and that all rolls are independent. Right? That's true of dice generally. So how would that work out? Well, our probability of success in this case is the probability of a 4. Being very careful in defining the sample space first, even though this is an easy question for us now. With the dice, we have 6 equally likely outcomes if the die is fair, and the 4 represents one of those. So our probability of success is 1/6. The probability of failure, which is going to be 4 complement, if I want to put it in those terms, is actually the whole sample space minus the probability of success. So that's going to give us 5/6. So that means that the answer to our question is pretty easy. I think we can do that right now. We're going to have the probability of failure times the probability of failure times the probability of success. So that means, I'm actually going to put it in this form. 1 minus 1/6 times 1 minus 1/6 times, let me make sure I stay on screen, times 5/6. Sorry, times 1/6. Work that out, and we're going to get 25/216. So that's the answer. So you better think about how much you're putting in and going to receive if you win before you decide whether or not that's worthwhile or not. Great. There's an example. Before I erase this and go on to the next part of the video, please make sure that you're picking up on something super important. If you've been studying statistics up until now, then you've probably gotten to the point where figuring out the probability of some certain outcome, like a 4, which we define as success, you're probably finding that that's pretty doable in most situations now, especially basic situations. As you get better, you can take murkier and more difficult situations and continue to find the probabilities of events like this. But the geometric probability distribution does not ask you the probability of some certain specific outcome, like the 4. This is the big point. The geometric probability distribution gives you the probability that it should take a certain number of trials before you achieve that first success. That's important, and that makes the geometric probability distribution kind of unique. What's the probability that it should take us such and such a number of tries before we get what we want? That's different, and it should be noted. Okay, let's go on to the next part of our lesson. So that's a basic example of geometric probability, the sort of situation that would lead you to want to utilize it. And we came up with an answer. Now we're going to talk about it more generally. We saw a couple of things. Okay. We saw that we had to, now I'm going to write this as a geometric probability question. To find out the probability that x, our number of trials, in this case, in geometric probability, that x, the number of trials, should equal 3, where p is the probability of success. We use p as a variable here, equals 1 over 6. The probability of that was probability of failure times probability of failure twice. In other words, let me write this correctly. In other words, we had 1 minus the probability of success to the power of 2 times the probability of success. Another way to write that would be the probability of failure to the power of 3 minus 1. This is how it's written. X minus 1 times the probability of success. We always take the power of failure, the probability of failure to the power of x minus 1, because we always imagine an unbroken string of failures until you reach that first success. So out of all the number of trials, the first x minus 1 are failures, and then finally you finish with a success, right? The generic formula for geometric probability is the probability of x is equal to 1 minus p, the probability of success, to the x minus 1 times the probability of p. And that's always the case for geometric probability. Great. I hope that's clear. Let's move on, now that we have the general form, and go on to the next stage of what we're going to talk about. What is the lowest value that x can take on? Well, x is always going to be at least 1. X can't be 0 because it doesn't make any sense to talk about trying something like rolling a dice or flipping a coin. It doesn't make any sense to talk about that 0 times. So x is always at least 1. And x can go as high as you can imagine. It's possible for you to keep rolling that dice or flipping that coin or doing whatever it is that you're doing forever and never reach success. Now, after a couple of tries with something reasonable, like a dice, it's going to be pretty unlikely that you're going to go more than 5 or 10 attempts, especially with the dice, but It could happen. So we can plug in any number from 1 to up to infinity for x, and we're going to be able to calculate geometric probability for that. The geometric probability distribution is going to always look something like this. Okay? Where we're going to make this 1, not 0. Let me make my origin of my xy graph like this. This is the way I want to do this. So that's the number of trials on the x-axis moving to the right. 1, 2, 3, 4, 1,000, 1,000,000, and so on. The probability that there should be one trial is always p, because that's the probability of your first success. And if you have only one trial, you don't have to multiply it by anything, failure or otherwise. It's just going to be the probability of success. If you do have 2 trials, you're multiplying that probability of success by at least one thing that is less than 1. Remember, both p and 1 minus p, both success and failure, its complement, that's your sample space. So you add them together and you're always going to get 1. You can do algebra on that without me, and you can see that that has to be true. So each of these values, p and p complement, the probability of failure is going to be less than 1. So each time we multiply again by failure, we're going to find the probability of the graph that we're looking at going down. It starts out less than 1, or possibly equal to 1 if the probability of success is 1, but then your probability of failure is 0. So it's at most 1, and generally it's going to be less than that, and then it drops from there, because as you go through more trials, you're multiplying by some value less than 1. So it always looks something like this. It also extends to the right all the way to infinity. This part of the discussion told us that. It's never quite 0, and the whole area of this construction is always equal to 1, because that's a sample space. Does that make sense? I hope so. It's called a convergent function. So that's what the graph looks like. We generally won't need that just to solve problems, but that's just for a little background. Let's go on and move on to something else. I am going to give you a couple of problems, and then I'm going to pause the video, or you're going to pause the video, and we're going to work them out and go on to a few more. Let's say I want you to figure out the probability of a success on the first trial with a fair die. Okay? You can define success as a 4 or anything else that you might want. Make it a 5. How about the probability that x should equal 4 with a fair die? And then finally, among these first problems, I want you to figure out the probability of the first success on 3 trials with not a dice, but a fair coin. Okay, go ahead and pause the video. Please work that out. You have the formula. You can plug it in. You can figure out the necessary probabilities. You know enough about coins to be able to do that. And then we're going to answer them together. So go ahead and pause right now. Okay, I guess we're back. Let's work them out one at a time. The probability that we should require 1 trial would be, now I'm going to do this kind of formally. You're going to think that I'm doing this using redundant steps, and maybe so, but I'm going to plug in the formula anyway and see that it gives us a good answer. If x equals 1, I'm going to take the probability of the complement of success, failure, to the power of x, which is 1, minus 1. That's 0, times the probability of p. We're still defining P as being equal to 1/6 because it's a fair die. So I have some expression to the power of 0, that's going to give me a 1, times 1/6, and that's the answer. Simple? Okay, let's continue. The probability of 4. Let's make that clean. The probability that x should equal 4 is, now instead of using P, I'm going to plug in the probability of any outcome with a fair die, which is always going to be 1/6 if the die is fair. So that's going to be 1 minus 1/6 to the x minus 1 power, that's going to be 3, times the probability of success, 1/6. So what we have is 5/6 to the third power times 1/6. And that's going to be 5 to the third power over 6 to the fourth power. I'm going to let you figure that out. That is not a 64. That's 6 to the fourth power. Before anybody messages me, let's make that obvious. You can figure that out. Your phone even has a calculator on it, so you can figure out what that is, and that's going to be the probability. Last one, the probability of 3 with a fair coin. This one, maybe I'll come up with an answer. We'll see. The probability that x should equal 3 with a fair coin. So the probability of P is the probability of whatever we consider to be a success with that coin. I always seem to settle on heads, so let's go with that. It's a fair coin, so that's going to mean one outcome out of 2 possibles. So the probability P is 1/2. So what we have if we plug it into the formula is 1 minus 1/2 to the power of 3 minus 1 times 1/2. The probability of failure to the power of x minus 1 times the probability of success. And that's going to give us, unless I'm really mixed up, 1/8. Simple? I hope so. Okay, let's go on to a second class of problems with geometric probability, or a second level of difficulty anyway. Let's go ahead and do this. Let me write them out. I'll explain them. And then we'll work out how to work them. First of our second group of problems, the probability that x should be greater than 3 with a fair coin. Also, the probability that x should be between 2 and, let's make it 4, inclusive with a fair die. Let me ask you to remember something. We treat inequalities differently when we're talking about discrete and continuous probability distributions. This geometric probability distribution is actually discrete. I drew it earlier with a smooth line because I wanted to show the sort of curve that it represents. And there are ways to cook up mathematical methods for representing it as a smooth line. So I'm not completely on shaky ground there, but in its basic form, it's really a discrete probability distribution, isn't it? So there would be a big difference between what I've written here, what I've asked us to work, and this. This is totally different. With a discrete distribution, if I'm saying x is greater than 2, but it's less than 4, then that would mean x is only equal to 3. And we worked that out before. And we don't need to do that now. Let's try this way. Let me just remind you before we all pause the video and work it out before coming back. If x is greater than or equal to 2 and less than or equal to 4, that really means that you're taking into account three possibilities. The possibility that x would equal to 2 or 3 or a 4. So okay, go ahead and pause the video and we'll come back and work them out. Okay, we're back. I think we're back. Let's work these out. I'm going to start with the top one first. So the probability that x is greater than 3. Now remember what I drew for you as the curve. It's something that starts out a fairly relatively high number, even though it's less than 1, because it's the probability of success, and then scoots to the right and dwindles forever. How are we going to figure out the probability that x is greater than 3? We're going to be able to figure that out. Let's take a look at the sample space for the number of rolls of the die it would take us to get a success. Let's think about it. We could get a success on the first. We could get a success on the second roll. We could get a success on the third or the fourth or the fifth, etc., all the way to whatever number you want to visualize, all the way to infinity. And that's our sample space. That total chunk, the sum of that is going to be 1. So what are we going to do to answer this question? Well, if we're being asked the probability that x should be greater than 3, we want the sum of these probabilities. What we don't want are those probabilities. So let's use that very, very useful strategy in math where instead of figuring out a difficult sum that we do want, let's figure out an easy sum that equals what we don't want, subtract it from some known greater whole, and we're going to get the answer. So what we're going to do to answer this question is figure out the probability that x should be equal to or less than 3 and subtract that from 1, and that'll be our answer. So let's do that. What's the probability that x should be less than 3 with a fair coin? Well, that means we got to figure out the probability that it would be 1. The probability of 1 is simply the probability of success. You can try that, plug it into the formula with a fair coin. I might have said fair die earlier, but I meant for this problem to be with a fair coin. The probability of 2, part of our unwanted set, is going to be the probability of failure once times the probability of success. I'm cutting corners here. Please plug it into the formula and work it out. You may want to get that practice. And then finally, the probability of 3 is going to be the probability of failure to the power of 3 minus 1 times the probability of success, which is going to be 1/2. So what I have altogether is, I'm going to sum these right here. I have 1/2 plus 1/4 plus 1/8. And that's actually 4/8 plus 2/8, that's 1/4, plus 1/8. So the answer here is going to be 7/8. Did you get that answer? If you didn't, back it up, try it on your own, and then listen to the explanation again. I hope that explanation worked for you. Let me know in comments or messages whether it wasn't a good explanation. Let's go on to this one, and now I think we can probably see how to do this problem a little bit more easily. I'm going to erase this and make some space. Okay. You know, I need to finish that problem. This problem. We found that the probability of 1, 2, and 3 was equal to 7/8. So that means that the probability that x is greater than 3 is going to be equal to 1 minus 7/8, and that's going to be equal to 1/8. Okay, now we have the answer. I almost passed by that without giving us the final answer. That's it. Now we're ready to do this one. Let me make space. Okay, so the probability of 2 and 3 and 4 with a fair die. So what I need to do is figure out those probabilities and sum them. The probability of 2 is going to be the probability of failure, 1 minus 1/6. I just wrote 5/6 there, to the power of 2 minus 1. So I won't write an exponent, or I could write a 1 there, times 1/6, the probability of success. Here we have failure 3 minus 1 times, 2 failures, and then a success. I want you to see this pattern. The probability of 4 is going to be 4 minus 1 as an exponent on the probability of failure times the probability of success. So what do we have? We have something which, as we increase the number of trials before the expected success, we really have the same expression which continues to be multiplied by 5/6, the probability of failure, ever greater times. So for example, here, for this, I have 5/6 times 1/6. That's going to be 5 over 36. In this case, for the probability of 3, I have, and we figured that out earlier, 25 2/16. Okay. And then for the probability of 4, we actually have 125 over, that's 6 to the 4th. So guys, let's go ahead and sum these up and figure out what the final answer to this one problem is, okay? Let me go ahead and do this. So what we have is, and I had to pause production of this video to calculate what 6 to the 4th is. So 5 over 36, 25 over 216, and 125 over 1296. We have to add that up, 1296. So what we have is 5 over 36 converted to a fraction with 1296 on the bottom. And that's going to be 180, if I'm not mistaken, over 1296. 25 over 216 is going to be, you know what I'm going to do? This is a classroom technique that I use a lot, and I'm going to actually use it now. If I'm making an error here, because this I'm doing on the fly, you go ahead and you message me. Send it in a comment or in a message. We'll figure it out and I'll correct it. So the sum of these three values is going to be the answer to this problem. And if I'm not confused, I think it's going to be 455 over 1296. So that's the answer. That's the answer to that one. Hope that's clear enough. Let me go ahead and make a little space, and I'm going to propose another question. I want you to work on this, and I'm going to make another video to answer it, assuming I have enough interest. If more than 1 or 2 people messages me or sends me some sort of, like, you know, makes a comment that they want to know the answer. Okay, so let's try this. I want to propose that we have some coin out there where the probability of heads, and this is not a fair coin, the probability of heads is equal to 2 times the probability of tails. Remember what that means. That means the probability of heads is equal to 2 times the probability of the complement of heads. So given that that's the case, that's our funny coin, it's definitely not a fair coin, I want to know the probability, given that we'll define success as the first heads. What is the probability that X, the number of trials to achieve the first success, should be equal to or greater than 4? Okay, so try that out. And like I say, if there's a need or a desire or an interest, I'll make a follow-up video to answer this. Thanks a lot.